everybody.
Hi, hello.
Hello.
I've opened up the audience.
You all have my name, which I forwarded to this. I have now many faces.
Yeah.
Yeah, I hope it's fine.
Of course. For me, it's fine.
I will just put the poster on the screen and I will give a 2 or 3 minute introduction at 8:30. I mean, in 3 minutes time. Do you see the poster on the screen? Yeah.
Yes.
Yeah, great.
Yeah.
So let us start. It's 8:30 in India right now at night, and it is 10 a.m. in the morning in East Coast in US. And welcome to everybody. Good day to everyone joining us from different parts of the world. I hope you can hear me. Jürgen, are you able to hear me?
Yes. Yes.
Okay. So Professor Jürgen Kurz and I are organizing this webinar series as a part of a joint initiative between IIT Madras and Potsdam Institute of Climate Research, Climate Impact Research, PIC, Germany, as you know it. So the aim of the webinar series is to disseminate the state of art in the complex system theory, because right now we are all in the middle of, I don't know, second wave, third wave, fourth wave in different places, so hard to travel. So we thought we will make an effort to do this. And we intend to bring together experts ranging from a wide range of areas, wide variety of fields such as physics, ecology, climate science, engineering, and really good people, top people who have bridged the scientific discipline and led the way in developing and applying these aspects of complex system theory to real life problems. The series will present an opportunity to foster collaborations and promote interactions. Normally these things happen in a conference, but those opportunities are less now. So we'll hold the webinar in the last Monday of every month, and we are lined up eminent research from various areas. The last two talks were given by Professor Kurtz and Professor Aihara, and today we have Professor Edward Ott from the University of Maryland giving this talk today. And this is going on a auto loop. Professor Edward Ott's current research is in the basic theory and applications of nonlinear dynamics. Some of his current research projects are in wave chaos, dynamics on large interconnected networks, chaotic dynamics, fluids, and weather prediction. Professor Ott is a fellow of the American Physical Society, the Institute of Electrical and Electronics Engineers, and the Society for Industrial and Applied Mathematics. He is the recipient of APS Julius Edgar Lilienfeld Prize for 2014. And Professor Ott will speak today about the prediction of chaotic dynamical systems using machine learning. So I will stop sharing now. Professor Ott, the floor is all yours. You could share your screen and start the webinar. Are you able to share the screen? Yeah.
There we are.
Yeah, fantastic. Yeah.
Okay, hello everyone. I'm very happy to be here in this very nice webinar series. So I'm going to be talking about prediction of large spatiotemporally chaotic dynamical systems using machine learning. And the types of systems that I'm interested in, you could just think of weather forecasting as an example. It has very complicated boundary conditions, mountains, oceans, continents, and these occur on all scales. And it is really quite a difficult problem. My co-workers in this are Troy Akamano, Sarthak Chandra, Rebecca Fussell, Zhijin Liu, J.D. Pathak, Alex Wickner, Michelle Gervin, Brian Hunt, and Istvan Sunya. Let's see. How do I can't, let's see. There we go. So, let's see, I want to get rid of this top. Click on it. No. Okay. The general setup for this talk and type of machine learning that we use is illustrated here. The machine learning device is in this blue box. It gets an input and it has an output. And the box represents a complex nonlinear input-output relationship with a very, very large number of adjustable parameters. Based on many examples of inputs and the corresponding desired outputs that you would like to see, the training will adjust the parameters in the box so that you get a best fit to the desired output. And then after the training is over, you hope that this relationship between the input and the desired output continues. Having trouble going from one slide to another. Yeah, okay. Let's see, I want to get rid of this thing on the top.
Oh,
Okay, well. Oh, you got it. So what I'm going to be interested in is machine learning applied to dynamics. And dynamics is the study of dynamical systems. And a dynamical system is a system whose state evolves in time and for which the future evolution of the system state depends only on its current and past states. So an illustrative machine learning task in dynamics is the following. Given past state dependent measurements of an evolving unknown dynamical system, and I emphasize the word unknown, we want to predict the future evolution of those measurements. So all we're given is the measurements, we know nothing else, and we want to predict the future from that. And the bottom of this slide shows one setup for doing this. You have some training data, these measurements. So you could say that my input is a state of the system at time t, and my desired output is the state of the system at a slightly later time, t plus delta t. And we can then do the training and do this over the whole length of the available training data, that is the measurements that we've taken. Then when the measurements come to an end, say they come to an end at some given time, at that time, the input of the system will be the measurement and the output will be unknown. And we do this time delta t prediction. And so we get an output that we hope is a good approximation to what actually happens. That is, it's a good prediction. But then we no longer have the inputs, so we feed the output at time delta t in the future back into the input, and it produces a new output, which will now be at time 2 delta t. We then feed that back in, we get an output at 3 delta t, and so on. So that will give us an arbitrarily long string coming out, but it's not necessarily clear that arbitrarily long string will be a good prediction. In particular, it may start out as good and then not be a good prediction. And this is particularly the case if the system that generated the training measurements was chaotic, because that chaotic system is going to sort of be copied by this closed loop input fed into, rather output fed back into input system. In fact, the system on the right is itself a dynamical system, and it's a dynamical system that mimics the original system that produced the measurements. And since that system was chaotic, the predicting system is also going to be chaotic. And therefore, some small error in the initial condition will be amplified exponentially as the prediction proceeds, and we expect the prediction to break down. So, the type of machine learning that I'm going to be using in this talk is called Reservoir Computing. I'm going to describe it for you. In our work, we use Reservoir Computing, and there are two reasons for this choice, both having to do with scaling of the scheme or schemes that that I'm going to be talking about to the very large prediction systems that we envision. And the attributes of reservoir computing that attract us are that, first of all, that the training times for reservoir computers can be very fast. And we'll see why in a minute. And the second is that recent research shows the opportunity for advantageous hardware implementations, say using photonics and lasers or field programmable gate arrays. We're sort of anticipating that research will proceed and be very beneficial for the scaling up of the prediction systems to very large sizes. We note, however, that the schemes I'm going to describe can also be based on other types of machine learning, such as deep learning types based on backpropagation. So here is the outline of the rest of my talk. First, I'm going to discuss reservoir computing and its application for prediction of dynamics on rather small systems. And it will turn out that this is not good enough for us, and we'll have to extend it. And then I'll discuss how we extend it and give an example of the extension to weather forecasting as an example of a large spatiotemporally chaotic system. And then I'll give a conclusion. So as it says here, the first thing I'm going to talk about is using reservoir computing for prediction. So to start out with, as the name of reservoir computing implies, a reservoir computer has within it a component called the reservoir, and the reservoir is basically sort of a complicated, complex dynamical system and it isn't too critical what kind of a complex dynamical system it is. And that is the reason why many physical implementations are possible for reservoir computing. And it's possible that one or the other of these implementations is going to be very attractive. They've already been found to have attractive features. But in this talk, the realization of the reservoir that I'm going to be talking about is as a directed weighted network with capital D neuron-like units, which are the nodes of the system. And each node, let's give it an arbitrary node, the subscript or the identifier I. Each node has multiple inputs and outputs, and it has a scalar state. And the entire state of this reservoir component is given by this vector R of t, and each element of R of t gives the state of a single node. So the ith element of R of t, the vector R of t, is the state of the ith node. And here I'm assuming that each node has a state which is just one number, it's just a scalar. And then the network of connections between the nodes is given by a D by D adjacency matrix, A, such that the strength of a link from node J to node I is the matrix element Aij. So that is my description of the reservoir. And the reservoir is going to have some dynamics if it runs on its own, but we want that dynamics if it runs on its own with no inputs to decay to zero. Then we want to couple in this signal U of t that we're getting for doing the training. So this U of t on this slide is the same as the U of t that I mentioned on the bottom of this left of this previous slide. So we couple this in through through an input layer that is just a matrix Wn. And what Wn does is it maps the U vector, which may have whatever dimensionality it has, it maps it into the vector space of d-dimensional vectors, which is the space that R of t lies in. So Wn operating on U is in the space of the reservoir states. And we then use that as an input to the reservoir to drive it in some sort of a dynamical way. And the dynamics of the driving is given by this equation in the red box. And it's given, as I said, by this equation. And on the right-hand side, you have the hyperbolic tangent of an argument, AR plus WU, where AR plus WU is a vector in the d-dimensional space. And the hyperbolic tangent is also a vector in the d-dimensional space, where each element of the hyperbolic tangent of its argument is the hyperbolic tangent of the element of the argument that corresponds to the element of the hyperbolic tangent of the argument. And then we evolve the R of t according to this equation. So we go one step forward in time, each iterate, and we generate an orbit for the R vector when during the input of the training data U of t. And we then see what R as a function of t is, and what U as a function of t, and we take these values and we put them, say, in a digital computer and store them. So we have each R of t and the corresponding U of t at the same time, and we're going to use this for our training. So that brings me to the next slide. So what we want is, now we want to get an output. So we couple the state, the evolving state of the reservoir into an output vector using this output layer that's shown as the pink rectangle on the right of the reservoir. And it is, again, just a constant matrix, just as the Wn and the A were. And it maps the R vector, which has a dimensionality d, And generally, D is very large compared to the dimensionality of the state vector U of t. And so we're going to have this W out, map the R vector into an output vector V, which has the same dimensionality as U. And we want the output V of t plus delta t to be a good approximation to U of t plus delta t that we know from the training data if we're in the training phase. So here, if you look at the top red square, the training is the training phase is occurring over the interval of time minus t to 0. And then at time 0, we're going to start the prediction. At any rate, once we have these training U and R recorded values, what we do is we play with the W out matrix until we get V to be a good approximation to U. So we get the output that we want, or a good approximation to the output that we want. And the way we do that is we take the output going down to the box on the bottom here. We take the output, which is W out operating on R. We subtract what we want that to be. We want it to be equal to U of t. And if it was equal to U of t, this minus that would be 0. We then take the magnitude squared of this d-dimensional vector and sum those magnitudes over the training time, little t equals minus capital T up to 0. And we also put in a Tikhonov regularization term to prevent the, I should have said, we then minimize this sum with this Tikhonov regularization term that penalizes very large elements of the W out matrix. And this is to prevent overfitting of the data. So once we've done that, this V will be a good approximation to the U, and we'll be able to then close the loop. And as it shows in the last red box, and generate a prediction for t greater than 0.
10.
And we hope that will give a good prediction where the R of t, or rather where the output is given by W out times these R's that are given during the prediction phase. So that's the basic idea. And let's now move to the second part of the talk, which is just an example of doing a prediction of a spatiotemporally chaotic system. So the example that I'm going to be using is the Kuramoto-Shevchinski equation, which is a partial differential equation in a single scalar variable y that's a function of space. And in this case, space is one-dimensional with a spatial coordinate x. And since it's a dynamical system, it's also a function of time. And you see here the partial differential equation, where the subscripts represent the partial derivatives. So for example, the term y with the subscript xx is the second partial derivative of y with respect to x. And then we need a boundary condition on this equation, and we're just going to use the simple periodic boundary conditions with some periodicity length L, and L is sort of like the only parameter that we have of this system. And then we're going to measure the time in units of the Lyapunov time. So for any given chaotic system, it will have a spectrum of what's called Lyapunov exponents. And that spectrum of Lyapunov exponents is a bunch of scalar values. Each value in the spectrum is a Lyapunov exponent. And we're going to be interested in the largest Lyapunov exponent. And the meaning of this largest Lyapunov exponent is if we start out with an initial condition that has a small error in it, that small error will increase by a factor of E in every Lyapunov time. So the defining attribute of chaos is this exponential sensitivity of predictions to small changes in the input. And then what we're going to do is we're going to solve on a digital computer for solutions of the chaos equation itself. And we're then going to take a string of time series of that solution that has a length capital T. That's the length of our training data. And we're going to consider that as simulated measurements. So we're going to then say, I have this string of time series. I derived it using my knowledge of the Kuramoto-Shevchenski equation, but we're going to pretend that that wasn't the case, that we really obtained it by measurements of some system, and we didn't know what the system was. And then we want to do the prediction based only on those, quote, simulated measurements without any knowledge of how physically that time series was created. So we're going to use this time series for the training to predict the future evolution without knowledge of the Kuramoto-Shevchenski equation itself. And to do that, we need then to make an input to our reservoir, that is this this vector u of t. And what we're going to do is we're going to say that the vector u of t has q components, where q is the number of grid points on a grid in X, going from X equals 0 up to X equal L. So we're going to take X value, we're going to take values of X at X equals L over Q, X equals 2L over Q, and so on up to L. And we're going to put those Y of X and T values into the components of the Q dimensional vector U of T that we were using as the input, and we were also predicting it as the output in the machine learning. For the example, we're going to take the spatial interval between the measurements this is the spatial interval in X, which is L over Q. We're going to take that to be rather small so that the measurements accurately approximate the continuous function y of X at a given time t as a continuous function of X. So there we have it, and we're just going to apply this reservoir computing idea to this system. And I'm going to show you now an application of this prediction for a system of length 60. So that this is pretty long for us, and that is going to be a problem for us because this is one-dimensional and this is not a nearly as complex a system as what we want to treat. So this top panel shows the time evolution of the that we would like to predict. So this is after the training, starting at a time, you can see the time is plotted along the horizontal axis as lambda max times t, and therefore this horizontal axis is in number of Lyapunov times, or as in E foldings of the error in the initial condition. And the top panel here has time, as I said, going horizontally. It has the spatial coordinate X going vertically from 0 to L, and the dependent variable y of X and t is plotted color-coded according to this color bar on the right. So the reservoir prediction is shown in the middle panel, and whoops.
So after Christmas, she's leaving in Colorado.
So somebody has their should put their mute on. So the middle panel is the reservoir prediction, and this is gotten using a fairly large reservoir with 9,000 nodes. Then the bottom panel shows the error in the reservoir prediction, which is just simply the y value from the top panel minus the y value from the middle panel. And what you see is, you see that in this bottom panel, you see a region at the beginning, say between 0 and 5, where there's a lot of green. And if you look over at the color bar, you see that the numerical value 0, which in this case for the bottom panel would be 0 error, is color-coded as green. So basically what we're getting for this chaotic system is we're getting good predictions out to about 5 Lyapunov times, or 5 E-folding amplifications of the error of the original error in the initial condition. And we regard this as being acceptable and pretty good. However, we desire the ability to treat much larger systems than this. And this potentially requires a vastly larger reservoir size. And it's just not practical. It could never really be done this way in the cases that I'm interested in, like for weather forecasting. So we need to do different. We need to fix this. So that brings us to our second extension, and that is a parallel approach for prediction of large systems. And actually, I'm going to be talking about two approaches that I'm going to use for this purpose of looking at more complicated systems. So the first one is this one that I'm going to talk about, and the second one is item C that I'll talk about next. And then I'll combine the two, and then finally at the end of the talk, I'll apply it to an example of a large spatiotemporally chaotic complex system through weather forecasting. Okay, so we're at item B, this parallel approach. So this picture on the top is a cartoon of what I'm going to do. So what I'm going to do is I'm not going to use one single reservoir. I'm going to use many reservoirs, and they're all going to be relatively small, but there's going to be a lot of them. And what this approach takes advantage of is a characteristic of these spatiotemporally chaotic systems that I'm going to be dealing with. And the characteristic is the following. So let's say I have a very large, complex spatiotemporally chaotic system, and I perturb it at some point and some instant in time. So I perturb the system, say at this point, and then I look at another point that's far distant from it. And my hypothesis is that the state at the other point won't be immediately affected by my perturbation far away, but it'll take some amount of time for the effect of that perturbation to travel over the space between the 2 points and affect the more distant point. So that's what I'm banking on for this approach. And so what I do then is I have all these many reservoirs. Each of them is going to predict just a few, just the evolution of a small region. So for example, this middle reservoir here is, as you see, I should have said that what these two horizontal lines are in the cartoon. So the bottom horizontal line shows, with the points on the horizontal line, showing the grid representing the state of the system at some time t, and the top horizontal line is all the same grid representing the state of the system at a time t plus a small increment into the future, t plus delta t. And what I want to do is move from knowledge of the grid points on the lower line to knowledge, to prediction of the state of the system on the grid points on the upper line. And so I'm going to assign, say, this middle reservoir or machine learning device the job of predicting a small region that I'm showing schematically as these two red points, both on the bottom line and on the top line. So the reservoir system, the middle reservoir system, is going to take the state of the at the various grid points that influence or determine the prediction at time t plus delta t. And those points that determine that prediction will be the two red points on the time t line, plus a neighborhood around it that's large enough to include all of the grid points that causally affect the state at the predicted time t plus delta t. And those points are the points that are being predicted themselves, plus schematically it's shown as 1 point over to the left. That is this blue dot that's being inputted into the middle reservoir through the red arrow, and the green dot being inputted to the reservoir on the right. And the important point here is that during this training phase, I'm training the outputs of many outputs, one output layer for each of these reservoir computers, and the training of these W outs is independent and doesn't interact with the training of the W out for another reservoir. So each training can be done for each of these individuals, can be done independently and in parallel. Okay, then once it comes time to do the prediction, the output is taken and then fed back to wherever it's needed. And this slide is showing where it's needed, that the outputs from the two reservoirs on either side of this one-dimensional domain of the middle red predictor feeds back in over there to provide the inputs in the larger domain. So once you're doing the prediction, the reservoirs are interacting, but in the training, they're not interacting. Okay, so now let's look at an example. So again, we're using the Kuramoto-Shevchinski equation, and but now I've made the periodicity length much larger, and in fact, I cannot apply the previous method that I showed you of using only one reservoir. So here I'm using, for my prediction, I'm using 64 parallel reservoirs. Each of these 64 parallel reservoirs has 5,000 nodes, so each reservoir is smaller than the one that I was using before, but there are many more of them. What you see now is the top panel again is the true state, the middle panel is the reservoir prediction, and the lower panel is the reservoir prediction error. And you're seeing green on the the lower panel over a time, there's a lot of green up to about 8 Lyapunov times. So that's 8 e-foldings. So I'm getting better results than I had before with the shorter, the smaller system, the L equals 60 system. I'm going out to 8 Lyapunov times valid prediction rather than whatever it was, about 5 before. So that worked well, but we're interested in situations where there, say, like weather prediction, where it is also practical, and indeed it works fairly well to do the prediction using a physics-based model embodied by say a partial differential equation system, and it could make weather forecasts also. And we know that it gives useful forecasts. However, we also know that these weather prediction codes don't include all of the physics, the subgrid scale modeling, there are errors, and that these limit the forecast. So the question is, can we combine machine learning and the knowledge-based system to do better than we would do if we were just using machine learning alone, just based on data, or if we were just using the knowledge-based system alone, which is mainly based purely on known physics. If we put both of those together, can we make a big improvement? So in the next few slides, I'm going to be discussing how we can do that. But to make the discussion simple, I'm going to talk about doing it with the simple machine learning, not using the parallel system, just using a single reservoir. Okay, so this shows the basic idea. So we're going to again have an input shown on the left as the left figure, the open loop configuration, shown as U of t. So U of t comes in, and you sort of have these two systems in parallel. The upper system, shown in red with the M on it, M for model, is the knowledge-based model, and the lower system with the rectangle WN and the reservoir circle is like the reservoir system. And then we're going to take an output simultaneously from both of them and combine them. So U of t comes in, it goes into the red box. The red box takes the U of t as an initial condition. It integrates it forward by an amount delta t, and then that comes out as an output, which eventually goes into the output layer. The U of t also goes into the input layer of the reservoir, which then evolves the R of t to R of t plus delta t, and then those R of t plus delta t go into the output layer W out. And the output layer W out then takes a linear combination of the R of t's from the reservoir and the prediction values made by the knowledge-based model. And the W out doing that combination of these two components is then determined by linear least squares fitting to the available training data that give you U of t plus delta t. So the W out is sort of combining these two components, the reservoir and the knowledge-based one, in such a way as to give the best result. So it's an optimal, in some sense, an optimal combination of these two approaches. And then once it comes time to do the prediction, we close the loop as shown on the right and feed the output back to the input and generate our prediction. And this now shows, again, using the Kuramoto-Shevchinski equation as an example, shows an example of that. So in this case, we're looking at the Kuramoto-Shevchinski equation, and the truth is shown as the top panel. That's the numerical solution of the Kuramoto-Shevchinski equation. And here the periodicity length is actually shorter than the 60, than the value 60 that I used at the beginning. So it's quite a bit shorter, and this is the result that you see on the top. And then in the middle, you see three panels. The top one is the reservoir error and the reservoir prediction error. And here I'm using a reservoir that's relatively small. So I'm using a kind of a tiny reservoir with only 500 reservoir nodes before I used 9,000. And then when I did the parallel, I was using 5,000. So this is very much smaller than what I used before. And because of the small size, the prediction, the solid green area is rather small. So if this vertical black line I'm showing is where is some way that we had for saying that the error is very tiny, and it just extends up to about a third of a Lyapunov time, so much less than what we had before. And then I'm going to show now in the middle of these three guys in the middle, I show the model, the error that the model makes in its prediction. And for this case, I'm doing the prediction with an imperfect model. So I want to make the model imperfect to simulate like some large system, which is not perfect, but this is a small system, relatively small system. So what I've done is I spoiled the true Kuramoto equation by which is creating the data and as well as the future evolution. I've spoiled it by changing one of these coefficients. It's just sort of an arbitrary thing to do. And what I did is I increased the coefficient of the second derivative of y with respect to x. I've increased that coefficient from 1 up to 1.1. So that's the coefficient 1 plus epsilon. And here epsilon is the error, and the error is about 10%. And when I do that, the prediction is really awful. It's only about a tenth of a Lyapunov time. So it's just like as if you just said that the initial condition didn't change. So, however, if I take now these two components, the terrible model and the very tiny reservoir, I then combine them in this hybrid, I then get actually quite a good prediction. So you're seeing, according to this black line criteria, it's going out to maybe 3.5 Lyapunov times. And if you look closely at it, you see you're getting really a lot of low error out to something like 7 Lyapunov times. So you're doing the hybrid is doing way better than either of the two components, and the combination is, it's really taking the best of each and combining them in such a way as to give something that's much better than either one of them. The bottom bunch of three curves is like the one above it, except that the imperfect model is much more perfect. It's only a 10% error, and the reservoir is much bigger, so it's also much more capable at prediction. But the main conclusion still applies. You get much better results when we do the hybrid. And I see I'm way over time. So let me I'm just going to skip number D, where we combine these two methods and make a parallel machine learning combined with a global knowledge-based system. And I won't go into it here because the time is short, and I'll just go to the last part, which is this application to weather forecasting. So what I'm showing here is in this paper by Troy Arcamano et al. It's not published yet, but it's available on the Earth and Space System Open Archive. And in this, we use, for the physics-based code, we used a code that's available called Speedy, and it has a reduced resolution relative to operational weather forecasting codes. In fact, it has about 3,700 grid points, but it still realistically incorporates the relevant physics for weather. It's three-dimensional, where the 3 dimensions are latitude, longitude, and height. It has built in the terrestrial geography. It has continents, oceans, ice-covered regions, mountains. These are all in the model. Then we need some data, and in this case, we're going to use real experimental data or observational data. So the data that we're using, we're going to use it for the machine learning training, and also importantly for assessing the accuracy of the forecasts. And it's obtained through a process called reanalysis by the European Center for Medium Range Weather Forecasting. Reanalysis is a process used to estimate the most probable atmospheric state from measurements that might be noisy, biased, and incomplete. When I say incomplete, I mean like you might have a measurement like balloons are let up and they go up in the air and they take very good measurements, but there are very few, if any, balloon measurements over large regions of the Earth, for example, the oceans. So that's what I mean by incomplete. We don't have measurements at all of the grid points on the model, but we do have these reanalysis estimates. And then for the ML component of our system, we're going to use 1,152 parallel reservoir computers, each assigned to prediction of its own local region, which is shown in this blue grid of squares. And it's going to, based on inputs from a larger region, shown for the middle blue square as the large red square, it's going to include neighboring inputs. And each local region, I guess, I don't know whether you can see this, but there's a grid of points, black dots in here, and each blue square has in it 4 2x2 grid points. And these grid points are occurring at every altitude level on the three-dimensional grid, extending from the ground level up to the top of the atmosphere. So our local regions are these 2x2 squares horizontally, and they extend this all the way up from the ground to the top of the atmosphere. In our future work, we're going to also localize in height, and we expect to get much better results when we do that. But for now, we haven't done that. And this shows 3 results taken for temperature in the mid-latitudes of the Northern Hemisphere. And each of these 3 panels is for a different amount of forecast in the future. The one on the left is for a 1-day forecast. The one in the middle is for a 3-day forecast. And the one on the right is for a 5-day forecast. And the 3 curves on these pictures are the mean squared forecast error averaged over the Northern Hemisphere mid-latitude and over some period of time for 3 different methods. One is the method where you just use the speedy code, the knowledge base code alone. Another is where you just use the parallel reservoir computing alone. And the other one is where you do this combination. And what you're seeing is the combination, which is the blue curve, is always further to the left, which is showing that since the RMS errors are plotted along the horizontal and the height above the above the ground is plotted vertically, we're seeing that we're getting substantially less error in our combination than in either or 2 of the components. And with that, I will finally stop and just show you my conclusions. With more research, we believe machine learning will become a standard tool for studying the dynamics of a broad range of high-dimensional, complex, chaotic systems. Our preliminary studies indicate the potential for greatly improving weather forecasting And just as a comment, we're now working on using this sort of same framework for predicting climate change. So thank you very much. And I'll just show as a conclusion some of our papers listed here using machine learning for nonlinear dynamics prediction. So that's the end of my talk, and I'll stop.
Thank you very much for this very nice talk. There were over 200 people listening to it. So my request to the audience is to type your questions in the Q&A box at the bottom of the screen so that it's hard to have everybody speak. So please type your questions on this Q&A box, and maybe the panelists can ask the questions directly. So there is a question from Ferrari Ricardo. How are reservoir nodes connected to each other initially? Are they connected at random as well? I'm reading all the questions.
Yes, so the A matrix, we use we just make a random connection for the A matrix with some given in degree, and that's how that's how we do it. So we also do use randomness for making the WN, but we have some specific things that we require of the WN. But we could change our use different random realizations, and it doesn't affect the results very hardly at all.
Thank you. There is a question from Professor Wolfgang Polifke. He asked, you described reservoir computing for autonomous dynamical systems. Are there equivalent comparable schemes for nonlinear input-output black boxes?
Yes, in this in this list of references that you have, the bottom reference actually indicates that. If you read the title, it says backpropagation algorithms and reservoir computing in recurrent neural networks for forecasting spatiotemporal dynamics. So if you look there, you'll see both deep learning and reservoir computing used together, and there'll be references to other deep learning papers.
Thank you. The next question is
similar things.
How is the adjacency matrix obtained? Does adjacency matrix update during training?
Could you say that again?
How is the adjacency matrix obtained?
So as I said, the adjacency matrix is a random network, weighted network that's chosen to have a specified degree. So every node has the same number of inputs. Otherwise, it's random, and the strengths of the links are also chosen randomly.
Okay, thank you. The next question is, how to choose the number of reservoirs in a single reservoir computer, and how to choose the number of reservoir computers in parallel reservoir computing?
So well, generally, for the single reservoir, it would be, if you're just using a single reservoir and you have enough resources, you might make the reservoir larger to make it more accurate. Or if there's noise, eventually, if you keep making it larger, it's not going to get any better. So, like the initial error will be determined by the noise rather than the ability of the computer. And if you have, so then you wouldn't want to make it any larger, because that would be a waste. With respect to the parallel system, we've done tests with parallel systems, and generally, if we keep the reservoir sizes fixed and increase the number of parallel reservoirs, the prediction time gets better and better and better. So again, you would like to use as much as your resources permit. However, if there's noise present, there will be a limit to how long, how good you could make the how long you can predict, determined by the noise rather than by the number of parallel reservoirs that you use. And you wouldn't want to be using more reservoirs than without getting any benefit from it. So those are the type of considerations that you would have for the answers to those questions.
Okay, thank you. Next question is from Thomas Burry. He thanks you for the wonderful talk, and he's wondering how the reservoir network approach performs with noisy data. I guess this is an important question. And he says, I imagine that the climate data was noisy, but have you tested this on models that include noise?
So yes, we have tested with noise. In particular, that the last results that I showed you on the atmosphere was from real data, and it certainly is noisy. So that's my answer.
Okay, thank you. From Sandeep, how much training length was used for a single reservoir? Also, did you check how the prediction time scales with the training length, training data length?
Yes, we have done that, and again, if you keep increasing the length of the training data, you you eventually will come to a point where you stop getting improvement. So and again, the presence of noise will affect the amount of data that is optimal.
Okay, thank you. This is a general question. Is it possible to obtain good prediction using low number of nodes? I guess.
Using what?
Is it possible to obtain good prediction using a low number of nodes? He wants to know how low.
If the number of nodes is smaller, the prediction, let's say there's no noise, the prediction will get worse and worse, or in terms of the amount of time you can predict in the future, as you make the number of nodes smaller and smaller. I should say that the thing that limits the number of nodes that you could use in reservoir computing is the training, at least the way we're doing the training. So I said the training is just a simple linear regression, and there's analytical solution for linear regression, which involves taking the inverse of the matrix, and the size of the matrix is basically the number of nodes. And this inverse is the limiting problem for doing this training because the difficulty in taking an inverse scales like the cube of the matrix size. So, once I guess you could get up to maybe, if you have a good system, you could get up to maybe 20,000 nodes, but past that, and even 10,000 nodes is very problematic. But if you're doing, say, 5,000 or 3,000 nodes, it's extremely fast. And we're thinking of these parallel systems where we're using, we're doing our scaling and using relatively small reservoirs. Even though the system is very large and complicated, we would hope to be using small reservoirs where we don't run into this problem and where we can do the training very quickly.
Thank you.
So that's the answer to that question.
This is an interesting question. Is from John Allen. Is there any advantage in using reservoir computing instead of deep learning based methods such as physics informed neural network or PIN? Would the accuracy be similar in both the cases?
I don't know specifically about physics informed neural networks. We haven't tried to use those. I don't actually know how I would make them scale to these very large systems. I'm not sure that it could be done for systems. The current weather forecasting systems are approaching 1 billion nodes, and I don't know that any. Well, I believe that our reservoir computing might be able to scale to the required resolutions for these tasks. And that's why we're looking at it. But as far as the physics informed technique, I have no idea whether it could scale, and I'm kind of skeptical, knowing what I know about physics informed neural networks. I'm skeptical that they could do the job.
Okay, thank you. Next question is, what would be the estimate of the upper limit of the prediction time of a good prediction predicted by the reservoir?
So the limit would be coming from the resolution and the noise and the measurements. It's now thought that current weather prediction, for example, it works fairly well for the times that are reported. We certainly find it useful, but people estimate that that there are the limits in it are could be pushed out if the the atmospheric modeling was improved. So that's sort of what we're going at.
Okay. Is there any repository of source code for the methods explained here?
We have. I don't think we've put that up yet.
Okay.
We certainly want to do that. That's on our list of things to do.
Okay. Next question is, did you compare high connectivity and low connectivity reservoirs?
For the simple system, the simple for predicting simple systems like the Lorentz equations or something like that, people have been very interested in sort of saying, can they do better by sort of by choosing the reservoir topology, the reservoir network topology in various kinds of given ways. And there have been a lot of studies on that. We have done some very small tries. We didn't find any big differences, but we haven't tried very hard. And probably, if you're interested in that, you should probably look at some of the other papers on that. There's one paper on that in the journal Chaos, which Jürgen is an editor of. And I think one of the co-authors, if you want to look it up, is actually two of the co-authors. One of the, I think some of the authors are Daniel Gauthier, Andrew Pomerantz, and Daniel Canaday have done a study on that. And there are others as well, but not by us.
Okay. How important is the synchronization phase between the reservoir states and the input data in your model?
Yes, even if we start when we start out, there's some small error in the initial condition, because we're starting out with the output of the reservoir, and it's almost what the training data has, and that will exponentiate. But even if we had the exact initial condition, the reservoir would be making a little bit of error on each step, and those errors would exponentiate, and that would be a problem as well. We did do a study where we took the incorrect, very slightly erroneous initial condition and used it in the actual model, and saw how long the prediction would go. And for the case, I could show it if you like. I have it in a slide on this but the main result was that the true the small error of the initial condition, the true evolution of the small the small error gave a slightly longer prediction time. So most of the prediction time error was coming from the initial condition and not from the error that was made subsequent to the initial condition.
Thank you. The next question is, how do we construct the reservoir? Which different strategies for choosing the connections, and how do you choose the values of the parameters that are there?
Well, I don't know. We just sort of try different things, and it's not very scientific. And we try it out and see which one gives the best results, and then we use that for the future for predictions.
One of the questions is on application of machine learning in plasma physics. Do you want to say anything about it?
I think that there's a lot of scope for this in plasma physics. It's certainly tokamak is a large, very complex, spatiotemporally evolving system, and studying plasma physics using machine learning is a great thing. There are lots of other problems besides predicting dynamics that could be applied to plasma physics. For example, designing stellarator coils and things like that would be could be very much helped by machine learning, and the speed of the computations could be greatly improved using various kinds of machine learning in plasma physics. Machine learning is just has applications in so many different areas of physics that it's going to be a real revolution, and which has already started.
Yeah, thank you.
In science.
I will give one more question to the audience before we go to panelists, and then we can maybe come back to the audience. So the last audience question for the time being is, do you think the usage of complex systems and machine learning has led to a huge jump in the accuracy of predictions offered by meteorological departments?
I wouldn't say that it's led to a huge jump, but I think it can. There's still a lot of, it's just starting out. There's still a lot of development and maybe even some new principles that have to be discovered. There's a lot of room for research, and I'm actually fairly confident that yes, it will lead to a big advance in both climate and meteor and weather forecasting research.
Okay, that's one interesting point somebody is making. Andrea Elizabeth, how does the hardware integration capabilities of reservoir computing help in predicting weather?
Well, I think we're going to have to make a very large system, and it would, I think, ultimately to make a very large system with a huge number of parallel machine learning devices, it's going to be economical and more efficient to make sort of special purpose integrated large system of parallel devices that are fairly small, and because they're small and relatively simple, it's going to, I think it would be nice to sort of stamp them out in sort of a nice manufacturing way. And I think they can also be by using these physical implementations, they could be, as well as being cheaper, and I think they could be much faster as well. And there's already been indications that they can do these calculations very, very fast. Speed is particularly important for climate, because if you're gonna be, taking time steps that are 1 hour and you want to cover 10 or 20 years, that's a lot of time steps. So speed becomes more important. And I think using these physical implementations will, in the future, I think it'll be better than implementing it, sort of simulating the complex system on a digital computer. But that remains to be seen.
Yeah, that's interesting. Thank you. I will now request the panelists, you can unmute yourself and ask your questions or give your comments.
Yeah, Ed, this is Lou Pecora.
Yeah.
Hi, Lou.
Hi, good talk, by the way. I always enjoy it. Just a comment, and I am not an expert in deep learning. You might know a lot more than I do because you've been in touch with this. But regarding the question of how does it compare to deep learning, that is, how does reservoir computing compare to that? Maybe you mentioned it, and I missed it. But I think in deep learning, you're also tinkering with the network itself to make the system work very well, which you don't do in reservoir computing. It's just fitting that output linearly, which is a much more simple situation and faster.
Yes. Yes, that's sort of what this. On the other hand, by using the back propagation, which is sort of working on many more connections that are available, you might think that you can get by with fewer nodes, but you're using you're adjusting connections and the structure of the network. So that's a harder job, but each of these ways has their advantages and disadvantages. And in the last paper in this list of references that I have up, it's making a comparison between different kinds of back propagation algorithms and the reservoir computing. And it's also comparing the different kinds of back propagation algorithms as well. So that's my answer to that.
Thank you.
Good, I like it.
Anybody else from the panel would like to make a comment or ask a question?
Hi, this is Ambika. This is very nice talk. I was just wondering, can machine learning help us to arrive at some idea about the nature of the equations underlying the dynamics?
Yes, that was not a topic of this talk. One of my students, who actually is sitting right next to me now, is sort of, that's what he's working on. And he, for example, has looked at the question of, if you have a network and you listen, you take measurements of all the nodal states, can you use machine learning to infer the network connectivity, the structure of the network that connects the nodes? This is actually a large problem, and there have been a lot of non-machine learning ideas for how to do this. But my student, his name is Amitava Banerjee, and if you like, you can look up papers by him on this subject.
Okay, thank you.
Any other questions from any of the panelists? Okay, there is one question in the chat box. Are there any conditions for applying machine learning to dynamical systems? I don't know what exactly.
Well, I you know, I think it's pretty useful. There are some I think this is really this question is really a question for further research. There's a lot of tasks that one could imagine in dynamical systems. For example, one could be prediction from data. Another one could be taking the data and then inferring something about the unknown system. I think there are a whole bunch of other tasks that one could look at, and which task you could do and which task you can't do is sort of up in the air right now, and is awaiting future research. And there have been a number of papers addressing different tasks that one might have that are of a dynamical nature. So there's a lot to do.
Thank you.
So for example, one of the tasks that we're interested in is climate change prediction. In climate change, you're interested in a non-stationary system. So looking at non-stationary systems is sort of something that hasn't been done very much by machine learning. And it's non-stationary because the amount of CO2 in the atmosphere is changing. Also, the thing that you're trying to predict is, in the case of weather, you're trying to predict the state of the system, and you're only doing it over a short time because of the chaos. So you're going to say, is it going to rain in 3 days? But in weather prediction, you're not predicting the state of the system. What you're trying to predict is the ergodic statistical properties of the system as it evolves because of this non-stationary input, like CO2. So that's a very different kind of dynamical task. How does the attractor of the dynamical system change as the conditions, as the physical conditions change? So there are a lot of problems where you're just looking at new situations, and I think it's exciting. There's a lot of things to be done.
Good. I think it's quite a bit of time now, unless anybody has any question to directly ask. I think, yeah, I see 2 questions now in the chat box. Do you use any data reduction technique before referring the data for the machine learning models in the event of large data set?
So do we do anything to the data? Is that the question?
Yeah, are you doing any data reduction technique before turning it over?
Oh, reduction. No, I guess so far we have not. We are, well, there is some data reduction in the fact that we're using a coarse grid, but we really would like to use as fine a grid as we can, because we know that that subgrid scale processes have a big effect, and sub-grid scale modeling is often, well, that's what's used in current weather forecasting, and we think it leads to substantial errors, and that's one of the reasons why we're using machine learning is to sort of make up for that.
Thanks. There's one last question. Why is your time range starting from -t instead of 0? No.
There's no reason.
Yeah. Okay.
It doesn't matter.
Yeah. Okay.
But the main thing is I should say, which I didn't mention, is we're going to have this input to the reservoir, and initially there's sort of like a transient time where the reservoir adjusts the input, and we don't include that transient time in our training data. We throw that away.
Thank you. Okay. Jürgen, would you like to say something to close the talk? Are you there? Anybody else have any comments? Otherwise, we can call it a day. Okay. I guess that's it. And the next talk in this webinar series will be on January 31st. We don't want to hold on December 31st, of course. So it's by Steve Brunton from University of Washington. Also, it will be on machine learning. So thank you, everybody. Have a nice rest of the day. Good night, good morning, good afternoon, wherever you are in the world. Thank you all. Thank you.
Thanks, Sujit.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Thank you.
Sujit, are you still there?
Yeah, I'm there. Hi, Ramesh. Hi, nice to see you. Yeah, you have a question?
Yeah.